We'll continue our discussion of interference by talking about standing waves. So standing waves occur when two waves that have exactly the same frequency traveling in opposite directions interfere with one another. A lot of times what happens is that a wave that is traveling in the forward direction reflects off of a surface and moves in the opposite direction, and when you get the frequencies just right, you can create standing waves. So you have to match the right frequency in order to get this. So these two waves have the correct frequency traveling in opposite directions, right? So the top wave is traveling to the right, the second wave is traveling to the left, and then the resultant of these two waves added together is down below, and this is the standing wave. So one of the important things about standing waves is that you have regions where the two waves that are interacting or interfering with one another always cancel out, and that's this location right here where the amplitude or the amplitude of the wave at that particular location is always zero, and that's called a node. The place where you have the largest vibration is called the antinode. So let's look at a couple of different pictures that show standing waves and talk a little bit more about it. So first, before we look at this, I want to show a picture. Here we go. Not this one. Here we go, standing waves. So I'm going to go ahead, I'm going to put this back to the first fundamental frequency, and I'm going to hit play. And what I have is I have an incident wave that's traveling in the forward direction, and then I have a wave that's reflected back in the opposite direction. And these frequencies are set up to be just the right values so that when the wave that's incident traveling forward and the one that's reflected back interfere with one another in such a way that you have a large amplitude in the center, large vibration here in the center, and at the edges over on one location you have a node which there's no vibration, the waves always cancel out, and at the other end you also have a node. This is the very first frequency for these two waves that you can get standing waves. And for the first frequency where that occurs, you have a node on both ends and an antinode in the center for standing waves on a string. So let's assume that these waves had a frequency of 10 hertz. That's not necessarily what they have here, but let's just, for the purposes of this, say that they have a frequency of 10 hertz. It turns out if you doubled the frequency at which these waves were traveling, so now my incident wave has a frequency of 20, and the reflected wave has a frequency of 20. Now I create standing waves again, except now I have two antinodes, and I have three nodes, one at the very center and then nodes at the very end. So standing waves will only occur at set frequencies, and then you can get additional, so the very first frequency is the fundamental frequency or the first harmonic, and then the other harmonics where you increase the number of antinodes are always multiples of the first one. So if the first fundamental frequency was 10, then the second frequency would be 20, and then if I change this again and I hit play, now the frequency is even higher. So if this one had been 10 and the second one had been 20, this one would have been 30. And now I have three antinodes, and then I have nodes at the end and then two nodes also in the center part. So one of the keys for standing waves is that you have to have an incident wave and a reflected wave going in the opposite direction, and that you get standing waves only for particular frequencies of these waves. So let's talk a little bit more about what those frequencies actually have to be. And I wanted to point out that you could actually create standing waves on your own if you had like a jump rope. And maybe you've even done this as a kid where you just kind of oscillate. You have one person hold an end of the jump rope and then you oscillate your hand with the other end of the jump rope. You can get sort of a large amplitude in the center. You can create the first harmonic. And if you continue to vibrate your hand up and down, you might be able to get the second harmonic, which is where you have two large vibrations occurring, and then a node where there's no movement in the center. So this is the second harmonic. In both cases, you've got the incident wave, and then you have the reflected wave back, and they're interacting with one another. So we have to match a particular frequency in order to get this to occur. So one of the things we realize is that the frequency of a wave the frequency of vibration depends on the speed that the wave travels and the wavelength of the wave. So if you have a string, the speed at which the wave travels is going to depend on what the tension in the string is. It's going to depend on the mass per unit length of the string. And so for a given string, the speed with which the wave travels is a constant value. But we can adjust what the wavelength is and thus also affect and change what the frequency is. So I know there's a lot on this picture, but here are standing waves with the different harmonics. So the very first picture where I have two antinodes and two nodes at the end and one antinode in the center, this is called the first harmonic or the fundamental frequency. The second one, where I have nodes on the end and a node in the center and two antinodes, is considered the second harmonic. And then essentially when I have three antinodes, it's three harmonics and four harmonics, and it continues along those lines. So if I go to my expression for frequency, for the fundamental frequency, the frequency is the speed of the wave over the wavelength. And I realize in my picture here that to create one whole wavelength, I would actually have to expand the length of the string and have another section. So my wavelength here, or my length of my string, I should say, is actually only half of a wavelength. Or another way we can say this is one wavelength would be twice the length of the string. So the wavelength is twice the length of the string. So for the fundamental frequency, I could figure out what frequency I would have to oscillate my string at based on how fast the wave could travel on that string and the length of the string. Part of the reason for going through this is so that we can see how these different frequencies are related to one another. So if I wanted to get the second harmonic, I realize that now I have one whole wavelength taking up the space of the length of the string. So if I go back here to my frequency for the second harmonic, the frequency I would have to use would be dependent on the speed of the wave and the wavelength, but my wavelength is now the length of the string. I notice that if I compare the second harmonic to the first harmonic, that here I have the second harmonic is the speed over the length, the first one is the speed over twice the length. So the second harmonic is actually, the frequency I would have to use is 2 times whatever the frequency of the first one was. So as I mentioned previously, if the first one, to create standing waves, if I had to use a frequency of 10 hertz to get the first harmonic, to get the second harmonic, I'd have to use a frequency of 3 hertz. I just said that wrong. I would have to use a frequency of 20 hertz. So 10 hertz, then 20 hertz. I was thinking ahead, and so we could continue with this. If we wanted to get the third harmonic, you can sort of see the picture here in terms of how many wavelengths I have in here, and essentially the wavelength is only 2/3 the length of the string. And so if you put all those values in, I see that the frequency I would have to use to get the third harmonic is 3 times the fundamental frequency, and it continues along those lines. So to get to the fourth harmonic, it would have to be 4 times the fundamental frequency. So again, creating these standing waves, you have a very set frequency where that can occur. If I find out what will work for the first harmonic, and it happened to be a value of 10, say, which is easy to deal with, the second harmonic would occur at twice that frequency, 20. The third harmonic would occur at 3 times that frequency, 30. And then the fourth harmonic and so on would occur as multiples of that first harmonic. So the last topic in this presentation is the Doppler effect. And the Doppler effect is basically an effect that occurs when a source or an observer, depends on, it doesn't matter which one, are moving relative to one another. And what happens is that when the source of a sound or the source of a wave is moving with respect to an observer of the wave, the actual frequency that the observer the frequency of the observer is different than the frequency of the source. So it's easy to think about this in terms of sound, but you may have heard the Doppler effect in terms of weather because they also measure things in terms of waves. So let's think about it in terms of sound. So suppose you had a sound source and it was moving towards an observer. what would happen is that the observer would actually hear the sound as being higher pitch than it actually is. And if the sound source is moving away from the observer, they would hear a lower pitch sound. So you may have experienced this before if you've ever been driving down the road and there's an ambulance approaching you from behind. You can hear the siren, and as the ambulance passes, there's a change in the frequency that you hear from that particular sound source. So I do have an example here, and let's see, the Doppler effect. So I'm going to go ahead and try this. I'm not sure if the sound will actually play very well because I am on my speakers and I'm going to disconnect them. So let's give it a try, and I'll play it and see if you can hear the sound. So one of the things that you probably noticed with this picture is that the waves actually changed in terms of how close they were together. We can do the same thing here with a helicopter. So we can do the same thing. Hit play, the helicopter sends out sound waves, and between each of these lines is one wavelength. If the helicopter starts to move towards the observer, we can see what happens to, well, let me put it back. Let's go back to 0. Maybe if I can get to 0 again. I don't think I can get to 0. Okay, we'll just go forward. So we can see what happens to the wavelength. So the wavelength from the observer here, the wavelengths have become smaller, and the frequency is inversely proportional to the wavelength. So the frequency that's heard by the observer is actually larger when the source is moving towards the observer. If I have the helicopter move away, right, the wavelengths become larger. And as the wavelength becomes larger, the frequency, they're inversely proportional, becomes less. So let's go back to our presentation. So when the sound source and the observer are moving towards one another, you hear a higher pitch, and when we're moving away from one another, you hear a lower pitch. So this is sort of just a summary of the Doppler effect. When the source is moving towards you, you have a shorter wavelength, and of course, since wavelength and frequency are inversely proportional to one another, that's a higher frequency. And when the sound source is moving away from you, you have a larger, longer wavelength, and the inverse relationship would be a smaller frequency. And these are just the links to those animations.